So let's take a look at triple integrals in cylindrical coordinates. So a typical looking integral in cylindrical coordinates will have an r, theta, and z, and then the region described is r 0 to 2, theta 0 to pi over 2, and z 0 to 4. Well, that's a nice, what we would call a cylindrical rectangular region. In other words, the limits on each of the variables are simply constants. Well, that simply means that we integrate with respect to the first variable. And so integrating first with respect to r, you can see we've got our r squared, whose integral would be r cubed over 3. So we would leave the z sine theta alone and integrate the r squared, and then substitute the values of r. So substituting a 2 and a 0 and subtracting, we get an 8/3. So then we want to integrate that with respect to theta. The integral of sine theta would be negative cosine theta, and you leave the 8/3 z alone. Plug in the pi over 2 and 0 and subtract. Then we integrate that with respect to z. And that would just be a z squared over 2, leave the 8/3 alone, and then plug in the 4, 0, and subtract. So the mechanics of doing the integral in cylindrical coordinates is exactly like it is in rectangular coordinates. You're just doing different variables. Now, we could use the properties that we learned back in the double integrals, since this function has a function of z, a function of r, and a function of theta, all multiplied together. We could split this into 3 separate integrals, do each one, and then multiply. We could also enter that very easily onto our TI-89. Now let's see how we set up an integral when we're given a description of our region. You can see here we're talking about the region that is inside the cylinder r equals 2 sine theta. So we'll draw us a graph in Maple of r equals 2 sine theta. So this is indeed the cylinder. That kind of jogs our memory. The 2 sine theta is a circle that goes out to 2 on the y-axis. That means it has a radius of 1. And it goes infinitely up in the z direction. And it's bounded by the r theta plane, which is the xy plane, and the sphere with a radius of 4 centered at the origin. Now again, using Maple, we can put these together to see what it is we're talking about. And so here is the region. This is a z simple region. So in setting up our integral, we would want to integrate with respect to z first. So here's our sphere with a radius of 4. X squared plus y squared plus z squared equals 16 is the sphere with a radius of 4. We need that in terms of z. And so we will solve this for z. Now since it's above the xy plane, z would be positive, so we will use the positive square root of 16 minus r squared. So there's our first variable of integration. Now, like we did with the rectangular coordinates, we need to describe the region where this is projected straight down onto, in this case, the r theta plane, which would be the xy plane. So here's what we're looking at that we need to describe as the region D. Now, describing that using cylindrical coordinates, which will be the same as describing that using polar coordinates, we have the r, which is going from 0 to 2 sine theta. Then we've got the theta. Remember, this is the one circle is 0 to pi for sine and cosine. If you did 0 to 2 pi, you'd get two circles. And so there's our setup on our integral. Now in this one, we're trying to set up the integral that's bounded below by the cone z equals square root of x squared plus y squared, which would look like this, and bounded above by the paraboloid z equals 2 minus x squared minus y squared, which would look like this. Now, you oftentimes have clues in the fact that both of these are given in terms of z, that this region should be z simple, especially since z is a function of x and y in both of those. However, there's the two together. And as you can see from the picture, it is indeed z simple. Any line passed through this region parallel to the z-axis would go through the blue cone and the red paraboloid, blue to red. So we will integrate first with respect to z, and we'll be going from the cone, that's the square root of x squared plus y squared, which we've got to fashion in polar coordinates, or cylindrical coordinates. So x squared plus y squared is r squared, and the square root of r squared would just be an r. Now the paraboloid, 2 minus x squared minus y squared, if we take the x squared minus y squared and factor out the negative, we can replace x squared plus y squared with r squared. So we're going from r to 2 minus r squared on the z's. And then, like before, we need to convert the remaining region, D. So we'll look down the z-axis, and we see the circle with a radius of 1. To describe that in polar coordinates, we simply notice that the r is going to be going from 0 to 1, and to get all the way around a circle, we got to go 0 to 2 pi. So finally, we want to see how we convert an integral given in rectangular coordinates to cylindrical coordinates. Now, this is a two-step process. We want to begin by converting the region. Then we want to convert the integrand. So, since our first variable of integration is z, and the limits on the integral start with x squared plus y squared. So we want z equals x squared plus y squared. And x squared plus y squared is r squared. So we would want z equals r squared as our lower limit when we go to cylindrical coordinates. And z equals the square root of x squared plus y squared, which is z equals r, is our upper limit on our integral. Now we want to look down the z-axis at the image in the xy plane of the three-dimensional object and then describe that in cylindrical coordinates. You notice here we're going from x equals 0 to x equals square root of 1 minus y squared, which is the right half of this circle with a radius of 1. And so to describe the circle in polar coordinates with a radius of 1, the right half that is, we want r to go from 0 to 1, and then we want theta to go from negative pi over 2 to positive pi over 2. So the z's are going from r squared to r. The r's are going from 0 to 1. And then the thetas were from negative pi over 2 to positive pi over 2. Now the next step would be to convert the integrand x, y, z. Of course the z just stays z, but we would need to replace the x with r cosine theta and the y with r sine theta. So there's our integral in cylindrical coordinates.